So moving into 5.4, we have to start by talking about a thing called a sampling distribution, where to get a sense of what a sampling distribution is, we're going to start with a basic example, where we're going to take the set 1, 2, 2, 3 as a population. It's a population of rare, not very numerous things, I suppose, so maybe we'll say this is a population describing critically endangered animals of some sort. But anyway, in here, well, we can look at what happens with this data set in terms of samples of size 2, where we have 4 things, and to get our samples, we're choosing 2 of them with no consideration for order, which means that we have 6 options. We have the first 1, 2, the second 1, 2, 1, 3, 2 with 2, the first 2 with 3, or the second 2 with 3, as our different samples that we can have. And then we can talk about, from each of these samples, the mean within each of our samples. We can talk about the mean of all of those, where we'll get a whole bunch of values that are pretty similar. We'll have 1 plus 2 over 2, which is 1/5. 1 plus 2 over 2 again, which is, not 1/5, excuse me, 1.5. I got a decimal switched with a slash. But anyway, for our second case, we'll have 1 plus 2 over 2 again, which is also 1.5. And then we'll have 1 plus 3 over 2, 2, 2 plus 2 over 2, which is 2, 2 plus 3 over 2, which is 2.5, and then another 2.5. And from these means, we can then describe what goes on in terms of how they themselves are distributed. We can make a construction called the probability distribution of sample means. That is, the distribution generated by the sample means themselves, where we have our 3 values x, the potential sample means, 1.5, 2, and 2.5, and based on how many of them there are out of 6 options, they each have a probability of 2 out of 6. And as a result, we could then make a construction using this distribution. We could then get a value called the mean of sample means. That is, we could get the average of the population of sample averages, which is really weird to say, but you get a value mu sub x bar, a mean of means, from that 1.5, 1.5, 2, 2, 2.5, and 2.5, divide by 6, because you got 6 options, and you get 2. So you have that the mean of the means of our samples is 2. And interestingly, we have that mean of sample means ends up being equal to the population mean. Thinking back up to here, we have 1 plus 2 is 3, plus 2 is 5, plus 2 is 8, divided by 4 is 2. And math a second. But the point is, our value mu sub x bar actually happens to be equal to our value of mu. And we could also think of a value that we call the standard error of the mean. I'm not going to compute this here because computing these values is a bit funky, but we could take the standard deviation of our distribution of values, the standard deviation in the sample means, which is really weird and has a funky notation that's sigma sub x bar, where that acts a lot like the standard deviation for a population, but in this case, we take that value and we divide it by the square root of our sample size. So we're dividing whatever we get by the square root of 2. And in the book, in the homework, you might get one more example of a problem like this, where you're going to go through and find all your samples of a certain size and talk about the distribution of them and the mean of your sample means and the standard error of your sample means. And it's kind of a tedious process, but it is important to see once like the sort of construction we're working with here, because this is the sort of thing we're going to be doing a lot of with our central limit theorem, with our big result here, because there's some really interesting behaviors that happen in terms of these values here that might not be expected if you just look at the distribution in itself. And that's what we'll be seeing next.